All right, so recall from classic geometry that a ray consists of a point, so like this, and all points extending in one direction from that point. An angle is the union of two rays with a common point called the vertex. So here, A would be our vertex. We will use Greek letters to represent angles, so common choices of our Greek letters are alpha, beta, gamma, theta, and phi. And phi has two forms, the classic phi and what's called ver phi, or just phi. It's just a different glyph for the same Greek letter phi. In classic geometry, angles are static. And what that means is that we have a union of two rays, and we will have an angle, and it's not allowed to change. The other thing in classic geometry, there is no such thing as the measure of a negative angle. It doesn't make sense. So you couldn't have a triangle that had an angle that had measure negative 30 degrees. So turns out that we need a more general definition of an angle. So we will view angles in the following way. So our starting point will be the ray that consists of the positive x-axis, called the initial side. So in this case, our initial side is going to be here and here. And a counterclockwise rotation is considered positive. So when we're talking about angles in trigonometry, if we move in a counterclockwise direction from the positive x-axis, we will consider that to be a positive angle. If we move in the clockwise direction from a ray, we would consider that to be a negative rotation. We will also consider all of our angles to be in standard position if the vertex is at the origin and its initial side extends along the positive x-axis. It turns out that angles are translation invariant. So if we had this angle anywhere else in space, if we use only translations, that is shifting in the x direction or the y direction with no shear, so no stretching or shrinking, we will preserve angles. So it is convenient for us to think of all angles relative to the standard position. In the event that it's not, we can just move it to the standard position and it will not change the mathematical computations. So the key point there is that angles are translation invariant, which means we can pick them up and move them wherever we wish and not change the value of an angle. All right, so let's start with our first example. So we want to sketch an angle of 135 degrees and negative 225 degrees in the standard position. So to help give us reference, we have a Cartesian coordinate system. So we really only needed the positive x-axis, but we'll go ahead and use this in this fashion. So our initial side with its vertex at the origin will be here, and we want to rotate 135 degrees. So just a couple of facts that we're probably familiar with. If we rotate all the way around, that would be a rotation of 360 degrees. So a circle, or all the way around, contains 360 degrees. So that would mean that the positive y-axis would be at 90 degrees. The negative x-axis is 180 degrees. The negative y-axis is 270. And if we had come all the way around, we started at 0, but we've now returned to 360 degrees. So if we want to sketch an angle of 135 degrees, we don't need to do this, but it may help. We notice that 90 degrees plus 45 degrees is equal to 135 degrees. So we know 90 degrees is straight up, and 180 is here, but 45 degrees is exactly half of 90. So that means we'd go to here, but then to get to 135 degrees, we would go to 90, and then we have to split 180 and 90 in half, because that's 90. So this angle would be the 45 degrees, and the entire angle from here to here would be the angle that we wished, which is 135 degrees. So that would be a graph of our angle in standard position. So its initial side is on the positive x-axis, where it will always be, and its terminal side is out here in quadrant 2, where it is 45 degrees from the positive y-axis here. All right, so let's take a look at our second angle, which is negative 225 degrees. So the first thing we want to note, since it's the angle is negative, we're going to rotate clockwise. So we're going to go clockwise instead of counterclockwise. And once again, if we take a look at it, we'll notice that negative 225 is negative 180 plus a negative 45, which would give us our negative 225, which is our goal. So negative 180 would be, I would start here, and I'm going to go backwards 180 degrees. So negative 180 would fall on this point right here. So once again, negative 180 is going to be at the same place as positive 180, so on the negative x-axis. And then I also need to go back another 45 degrees. So we'll notice if I go a negative 45 degrees from here to here, I'm going to end up at the exact same place where I was with positive 135 degrees. So it turns out that if I sketch the angle of a positive 135 degrees, I get exactly the same diagram if I sketch the angle negative 225 degrees. And this illustrates the following key point. So first of all, so fact 1, the representation of a rotation, aka an angle, is not unique. So that's one thing we need to be aware of. It is possible to represent the same angle or the same rotation in multiple different ways. So we call angles that have the same initial and terminal side coterminal angles. So we'll return to the topic of coterminal angles and how they are related to many things involving trigonometry. But for right now, we need to know that the representation of an angle is not unique, and we need to know that we're going to call angles that have the same initial and terminal side coterminal. So then fact 2 relating to this is two angles are coterminal if their difference is 360 degrees. So in symbols, angles alpha and beta would satisfy the following formula. Alpha minus beta would equal 360 degrees times n for some integer n. So that means if we subtract any two coterminal angles, they would be a multiple of 360 degrees, or an equivalent formulation would be that their difference is always divisible by 360. So let's go back up and look at our diagram. If we were to subtract these coterminal angles, what would we notice? Well, what is 135 minus a negative 225? Well, minus minus makes it plus. So then if we add them together, we get exactly 360 degrees. So they are a multiple of 360 degrees, and 360 divides 360 exactly one time. Okay. So now, we've been talking about degrees. So degrees are kind of like feet. And what I mean by that is they are a unit that we use, and it turns out that kind of like using feet, inches, and pounds in science, it makes things really, really difficult. So when we take science classes, we almost always use the SI unit system, which is the kilograms, meters, and seconds. It turns out degrees are kind of, well, they're exactly the same thing. They complicate the mathematics. And the reason for this is degrees are around for historic reasons. They originate from the Babylonian society. And the reason that there are 360 degrees in a circle is that the Babylonian number system is base 60 instead of base 10. And so it worked well with their mathematical number system. But it turns out degrees complicate things. So we're going to want to think about measuring angles in a different way. So what we're going to define is the idea of what is called a radian. So let's start off with our picture. So the circumference of a circle is pi times d, which would be 2 pi times r, because our diameter is exactly 2 radii. So this is the distance around the circle, and this gives the circumference of the unit circle as c equals 2 pi times 1. So a unit circle is a circle with radius 1, so if I were to walk 1/8 of the way around the circumference of a circle, well, where would I be? So we know that the distance all the way around is going to be 2 pi. So if I walk 1/8 of the distance, well, what would be the length of this arc? So in other words, how far would it be? Well, if I went 1/8 of the way around the circle, it would be 1/8 of the entire distance, which is 2 pi, which would be 2 pi divided by 8, which is going to be pi divided by 4. So the distance that I would have traveled around that unit circle would be pi over 4 units. So this distance would be pi over 4. So what is the measure of the angle from here to here? Well, 1/8 of a circle would be the same thing. So if I know that there are 360 degrees in a circle, and I went 1/8 of the way around, that would be 360 degrees divided by 8, which would give me 45 degrees. So now the question is, well, what is the proportion of the distance that I walked to the circumference of the circle? Well, my proportion in each of these cases would be 45 degrees over 360 degrees, which would be 1/8 of the way. Or if I took pi over 4 and divided it by 2 pi, making 2 pi a fraction over 1, I would get pi over 4 times 1 over 2 pi. Pi is reducing out, I would get 1/8. So either way, the proportion is exactly the part that I walked around the circle, which is 1/8. So the arc length, we get this idea. So let's talk about this a little bit deeper. So when we're talking about degrees, we're talking about the measure from the positive x-axis to this point. The idea of radians is, instead of thinking about things in terms of a degree measure as a rotation from a place to place, a radian is the proportion of the arc length to the distance around the entire circle. So a couple of things worth noting. Let's pretend for a minute that the radius of my circle was in feet. Then that would make this distance in feet, and it would make the distance all the way around the circle in feet. When I take the proportion of those two things, if I had feet here and feet here, my feet would have reduced out, and this would be a pure number. So this turns out to make computations mathematically simpler. And what I mean by that is degrees are what are called a derived unit. They are invented by humans for humans, just like feet are arbitrarily measured. If you go back in time, the unit of a foot was derived from a monarch from Europe about 1,500 years ago or so. So it's defined in terms of something that humans were defining it in terms of. Radians are independent of whatever measurement system we use, because they have this property, since it's a proportion, that they will always reduce out and we will get a pure number. It turns out that this is going to be required for certain mathematical computations. So relating this to that idea of distance, which is going to be called an arc length, the arc length S for a sector of a circle is S is equal to R times theta. That's our proportion of the distance traveled, where theta must be measured in radians. Using this definitions, radians can be extended to any circle, where theta is equal to S divided by R, defines the angle in radians, as the proportion of the arc length to the radius. On the unit circle where R is equal to 1, this gives that the measure of the angle in radians is exactly equal to the arc length. So that is really our key idea. Radians are the same as arc length on the unit circle. On any other circle, it is the arc length divided by the radius, so that the same thing happens that we were just talking about. If theta is equal to s over r, this is going to have units distance because it's an arc length. This is going to have units distance because it's the radius, and they will reduce out 100% of the time to give us a pure number. All right, so let's plot some points on the unit circle in radians. We need to find its proportion to the unit circle. So we know that the circumference of the unit circle is 2 pi. So our proportion of pi over 4 to the unit circle is going to be pi divided by 4 divided by 2 pi. So we go 2 pi divided by 1, so that's pi over 4, and just like we had in the previous example over 2 pi, the pi's reduce out, and this tells us we need to go 1/8 of the way around the circle. So this is going to be 1/4 of the way, half the way, 3/4, and then this is all the way around. So if I need to go 1/8 of the way around the circle, 1/8 is going to be halfway between 1/4 and where we started. So that's going to be this point right here is going to be this arc has length pi over 4. And as we saw above, that would be the same as the angle of 45 degrees. So in terms of radians, that angle would be pi over 4. All right, so now this time, it's also worth noting, before we do the next example, we could have done that computation on our calculator, right? That is not what I wanted to do. Right, we could go and put our proportion in, so then we would have pi over 4. So pi divided by 4 divided by 2 pi, and we get 0.25, or as a fraction, 1/8, or 12.5% of our circle, right? So for our next one, our proportion is this time is 2. So if we take our proportion of 2 over 2 pi, the 2's reduce out, and we get 1 over pi. Well, I don't know what 1 over pi is off the top of my head, so I go 1 divided by pi, and I get the following value. So 1 over pi is going to give me about 0.318. So in terms of, if I think of this as a percent, this is about 32%, and 32% of a circle would be about 1/3 of the way. So 2 radians would be 1/3 of the way around the circle. So if I were to divide this into thirds, that would be 1/3, and then down here, Nope. That's too big for a third. Third would be more like up here. And that would be 2/3, and then 3/3 would be over here somewhere, which would be all the way around. So then this distance would be 2 radians. So that would make this angle 2 radians. So then 4 radians would be the proportion 4 over 2 pi, which would be 2 over pi, which is going to be twice the value we just had here, right? So 63, or 2/3 of the way around the circle this time, which we conveniently marked in the previous part. So this one is about 64% of the way around, or 2/3. So that's going to be this distance right here. And that would make this angle 4 radians. So the distance all the way around is 2 pi. And 2 pi as a number is, well, pi is 3.14. So 2 pi would be about 6.28. So there's approximately 6.28 radians in a circle. So to go completely around, we would need to go 6.28 radians approximately. So when we went 4 radians, we went about 64% of the way around our circle. All right, so the next thing we want to talk about is the area of the sector of a circle. So if we know the measure of a central angle, how can, well, that should say we, find the area of the sector? So if the central angle is 90 degrees, or pi over 2, that would be a quarter of a circle. So we know that the whole area formula for a whole circle is pi r squared. Well, if we have only a quarter of the circle, it would be 1/4 pi r squared. If the central angle was 180 degrees, that would be from here to here, so that would be the area of half of a circle. So the area formula then would be 1/2 pi r squared. This suggests direct proportionality. So the area of the sector of a circle is directly proportional to the measure of the central angle in radians. So this suggests then that the area is equal to some number k times theta. So this is our direct proportionality. We also know the ordered pair, that when we go all the way around a circle, so 2 pi, that the area formula is pi r squared. So that's the area of a circle. So putting that in, we can solve for k. So we have pi r squared is equal to k times 2 pi. And we solve for our proportionality constant by dividing by 2 pi. Our pi's reduce out, and we get k is equal to r squared over 2. So we put that back in, so our step 3 in solving our proportionality problem is we put k back into our original formula. So a is equal to, and I'm going to write this as 1/2 times r squared. So 1/2 times r squared times theta. So this is the equation for the area of a sector of a circle. So we got this formula by using the fact that the area of a sector of a circle is directly proportional to the central angle. So to find the area of any sector, we can use this formula, and we need to know the central angle theta in radians and the radius can be in any units whatsoever. All right, so let's find the area of the sector of a circle with central angle 45 degrees. So the first thing we need to take note of is our formula says theta must be in radians. So our angle is not in radians. Luckily, in the previous few examples, we've seen the angle of 45 degrees a couple of times. So back here, when we first started talking about radians, we discussed that pi over 4 radians was the same as 45 degrees. Because our rotation from here to here was 45 degrees, and the arc length from there to there was pi over 4. So therefore, pi over 4 radians must be the same as 45 degrees. We'll talk about an exact conversion and how we're going to deal with that in a few moments. But for right now, we saw above that 45 degrees is the same as pi divided by 4 radians. So then, if that's the case, the area is A equals 1/2 r squared times pi over 4. So that would give us r squared, or pi r squared, divided by 8. So the area of the sector of a circle with central angle 45 degrees is pi r squared divided by 8 for any radius r. So if the radius were 1, the area would be pi over 8. If the radius was, say, 4, we would get 2 pi, because 4 squared is 16, and 16 divided by 8 is 2. So we can use this formula, but the key thing that we have to be aware of is that formula is only valid if our central angle theta is measured in radians. So before we could use it in this example, we had to convert 45 degrees into radians, and radians, which we saw in the previous example. So let's talk a little bit more about that. So what we want to talk about is the idea of dimensional analysis. So dimensional analysis makes it sound a lot more complicated than it really, really is. So the idea of dimensional analysis is conversions. So dimensional analysis formally is converting from one unit to another. So we see common examples of this all the time, and we use it often without ever thinking about it. So if I asked you the simple question, well, how many minutes are there in 3 hours, what would you tell me? You wouldn't even think about it. You'd be like, there's 180 minutes in 3 hours. Okay, so formally, what we mean by dimensional analysis is the following. We have what's called a conversion factor, which is derived from a unit fraction. So a unit fraction is a fraction that is equal to 1. So what I mean by that is the following. We have the following equation, which we know is true. So we know that 60 minutes is equal to 1 hour, because there are 60 minutes in an hour. So we want to convert this into a unit fraction. Well, since it's an equation, the fundamental rule of equations says we can do the same thing to both sides. So I can create two different unit fractions from this. So unit fraction 1, if I divide both sides of the equation by 60 minutes, I would get the following. Well, on the left-hand side, 60 and 60 reduce out, and minutes reduce out. So this left-hand side, anything divided by itself is always 1. So that would give me 1 hour over 60 minutes. So this is a unit fraction because it is equal to 1. I could also divide both sides of the equation by 1 hour. And if I divide both sides of the equation by 1 hour, this time the right-hand side turns into 1, because anything divided by itself is 1, and I would get 60 minutes over 1 hour. This is also a unit fraction. The key thing here is 1 is the multiplicative identity. So what happens if you multiply something by 1? Well, what's 5 times 1? 5. What's 10 times 1? 10. Multiplication by 1 doesn't change anything. So since multiplying anything by 1 multiplying by a unit fraction creates an equal object. So the key idea is that since unit fractions are equal to 1, if you multiply by 1, it doesn't change whatever it is. Because x times 1 is equal to x for every object x, because 1 is the multiplicative identity. So let's connect back to our original thing. Well, we know that there are 180 minutes in 3 hours. So if I take the expression 3 hours, and I multiply it by 1, but I'm going to use 1 as one of my unit fractions. So I can think of 3 hours as a fraction, and I want to reduce hours out. So since my hours are in the numerator, to reduce them out, I would need hours in the denominator. So I would select the second unit fraction, 60 minutes over 1 hour. Because if I do this, I would have 60 minutes over 1 hour. And then I would have hours in the top, hours in the bottom, and they would cancel out. And when we multiply fractions, we multiply straight across. So 3 times 60 times minutes would give us 180 minutes divided by 1 times 1 is 1, so we get 180 minutes, which is what we knew we should get. So 3 hours has to be equal to 180 minutes. And we got that by multiplying by 1, aka our unit fraction, converting from hours to minutes. And I know you're probably thinking, well, why would I go through that whole thing when I can just figure out that one in my head? Well, it's true. That one's pretty simple, and we could figure it out in our head. But we are going to run into examples where we're going to have to chain together 2 or 3 unit fractions. You will not be able to do those in your head, most likely. So we would need to be able to do this dimensional analysis and decide which unit fraction to use, especially when our chains start getting a little bit longer. So putting this together with our desire from the previous problem to be able to jump back and forth between degrees and radians, we do know a couple of things that we can chain together. So we know that a circle has 360 degrees, but it also has 2 pi radians. Because the distance all the way around the circle was its circumference, and we know that the number of degrees to go all the way around a circle is 360. So this gives us that 360 degrees is equal to 2 pi radians. So the unit fractions are, if we divide both sides by 360 degrees, we get 2 pi radians over 360 degrees, which would reduce to pi divided by 180, and then we would have radians over degrees. And if we do our division the other way, if we divide both sides by 2 pi, we get 1 is equal to 360 degrees divided by 2 pi radians, and we get 2 goes into 360 180 times, so 180 over pi, and this time we have degrees over radians. So this one converts, the top one converts from degrees to radians. And this one converts from radians to degrees. And the reason for that is whatever is in the denominator of our fraction is what is going to reduce out, like what we saw above. When we had 3 hours and we wanted to convert it to minutes, our hours were in the numerator. So to reduce them out, we put hours in the denominator in our unit fraction. So that's why we selected 60 minutes over 1 hour as opposed to 1 hour over 60 minutes, is we wanted them to reduce out. So if our units are in the numerator and we want to reduce them out, we need to put the corresponding unit in the denominator. So in this unit fraction here, we're converting 2 radians from degrees. In the bottom unit fraction, we're converting 2 degrees from radians. So those are our 2 unit fractions. All right. So armed with that information, let's go ahead and do example number 4. We wish to convert 5 pi over 4 radians into degrees. So we have 5 pi over 4, and we have radians, and we want to convert it into degrees. So we want to go from radians to degrees. So we're going to select our second unit fraction. So it's going to be 180 degrees over pi and radians. Our radians are in the numerator and denominator, so they reduce out. We also have a pi in the numerator and denominator. So then we go and we simplify what is left. So we have 5 times 180, and we divide that by the 4 that's in the denominator, and we get 225. And our new units are degrees. So 5 pi over 4 radians is the same as 225 degrees. All right, so to convert 105 degrees into radians, we start with 105 degrees. And if it helps, we can turn it into a fraction. And since we want to convert from degrees to radians, we're going to use our first conversion factor. So we have pi radians over 180 degrees. So pi radians divided by 180 degrees. Our degrees reduce out, and that gives us 105 pi divided by 1 times 180 is 180, and then we have radians. And we can take and reduce that, so 105 divided by 180, and get a fraction. We would get 7 pi over 12. So this is 7 pi over 12 radians. All right, so when an angle is measured in radians, the word radians, or rad, is not written. If an angle is given without units, always assume that the angle is measured in radians. So basically, this convention is telling us that our default should be to think in radians. Unless we are explicitly told otherwise, an angle will always be measured in radians. So if you ever see an angle without anything affixed to it, it is in radians. So linear and angular speed. The linear speed v of a point, a distance r from the center of rotation, is given by the formula v is equal to r omega, where omega is the angular speed in radians per unit time. In the above formula, the units of distance for v and r must be the same, and omega, once again, must be measured in radians. If it is not in radians, we will have to convert from whatever it is in to radians using dimensional analysis. All right, so let's look at a couple of examples. So example 5, you recently changed your truck tires from a 30-inch diameter to a 34-inch diameter. If your speedometer indicates that you are driving 60 miles per hour, how fast is the truck really moving? If you think about what's going on here, you have a tire, and imagine you have some point P on your tire. When you drive, you want to know how fast you're going. That's a linear speed. That's how fast is your car moving in this direction. Your car doesn't measure that. Your car measures how fast is your tire rotating about its axle. That is an angular speed. So they are converting using this formula, V is equal to R omega. The problem is, if you change the radius of your tire, you are going to be changing how far you go in one rotation. So converting our diameters to radii, we're going to have r is equal to 15 inches, and we're going to have r is equal to 17 inches. So one rotation at 15 inches, or the circumference, would be 2 times pi times r, which is 15 inches, would mean you traveled 30 pi inches. But one rotation, if the radius of your tire is 17 inches, would mean that you would have traveled 34 pi inches per one rotation, right? So if the radius of your tire increases and the number of rotations stay the same, you're going to be traveling farther because the circumference of your tire has gotten larger. So our question says, we changed your truck tires from a 30-inch diameter to a 34-inch diameter. If our speedometer thinks we're going 60 miles per hour, how fast is the truck really going? So we're going to need to figure out, well, what is our angular velocity, and then use it to calculate the linear velocity. So a couple of things we need to be careful with. The first thing that our formula says is that units of distance for v and r must be the same. Well, what's my speed given in? Miles per hour. And what are my radii given in? Inches. So we must convert inches to miles. So if I have 15 inches, I need to convert into miles. Well, I don't know what a conversion factor is for inches to miles, but I do know that there are 12 inches is equal to 1 foot. And then the one that we may or may not know is that 5,280 feet make up 1 mile in the imperial system, because that makes sense. So we now need to convert, so we have 15 inches, and I want to convert from inches to feet. So in my unit fraction, feet go on the top and inches go on the bottom so that they can reduce out. And then I need to go from feet to miles, so I'm going to need to put feet in the bottom. So 1 mile over 5,280 feet. And then my feet reduce out. So now my units, the only thing that's left are miles. So then we would multiply across the top. 15 times 1 times 1 gives me 15. And then I can make that a fraction over 1 if I need to. 1 times 12 times 5,280 gives me, well, it helps if I multiply by 12 instead of 1. Gives me, let's try that again. 12 times 5,280 gives me 63,360. And then we can reduce that. So 15 divided by that answer, and we want a fraction, gives us 1 over 4,224. And similarly, we need to do the same thing. So 17 inches, 1 foot over 12 inches, and 1 mile over 5,280 feet. Once again, feet reduce out, inches reduce out. So if we multiply across the top, this time we have 17 times 1 times 1 over multiplying across the bottom, 1 times 12 times 5,280. And we get the following value, which I am going to store into my calculator for later. So let's store that as A in my calculator. All right, so now we need to figure out, well, how fast our car thinks it's going. So we have V is equal to R omega. So if we divide by R and divide by R, we get our angular velocity is equal to V divided by R. Well, our angular velocity is 60 miles per hour. So we have 60 miles per hour, and then we need to divide that by our radius, which is going to be this guy, 1 over 4,224 miles. So then our miles reduce out, and we invert and multiply, and we are going to end up with the following. 60 times 4,224 gives us 253,440. And that's going to be radians per hour if you're curious, but we omit radians because it's not needed. So that's how many times our tire is rotating per hour. So then to find out our velocity, our actual velocity, we're going to use V equals R omega, where we just found our omega here. And our r is going to be this r that we saved in our calculator as a. And that's going to be our r. So it's going to be the number we just found on our calculator times the a that we saved in our calculator, and it gives us 68. So that would tell us then that the actual speed of our truck would be 68 miles per hour. So if you changed the radius of your tires, or the diameter, by that much, your speedometer at 60 miles an hour would be off by 8 miles per hour. So if you thought you were driving 60 miles an hour, you would actually be driving 68 miles per hour because of the difference in the radius of your tire. All right, let's take a look at another example. So in example 6, a water wheel has a radius of 10 feet. If the water wheel rotates 14 times in 1 minute, what is the speed of the river in miles per hour? So we've essentially got this water wheel, and we know that it rotates 14 times in 1 minute. So we have 14 rotations. It happens every 1 minute. Well, we need to figure out an angular velocity. Well, we need omega, but omega must be measured in radians. So our omega, this tells us that omega is equal to 14 rotations per minute, because it's telling us that we rotate 14 times every minute. But we need to convert from rotations to radians. Well, the distance all the way around a circle is 2 pi radians. So we know 2 pi is equal to 1 rotation. And if we want to reduce out rotations, our unit fraction needs rotations in the bottom. So we're going to get 2 pi divided by 1 rotation is equal to 1, and that's going to be our unit fraction. So we have omega is equal to 14 rotations divided by minutes, and we multiply by 2 pi radians over 1 rotation. And our rotations reduce out, and we get 28 pi radians per minute. We want to know, well, what is the speed of the river in miles per hour? So we have rotations per minute, but according to our formula for this, the units of distance for v and r must be the same. So if we have our velocity in units minutes, then we're going to get our answer in minutes. So we need to convert from minutes to hours. And we know that 60 minutes is equal to 1 hour. But this time it's a little bit different. Where are our minutes located? The minutes are in the denominator. So to reduce them out, we need minutes in the numerator. So we're going to divide by 1 hour and divide by 1 hour. And this gives that our unit fraction is 1 is equal to 60 minutes per 1 hour. So then converting again, we have omega equals 28 pi radians per minute, and we multiply by their 60 minutes per 1 hour. And now notice our minutes are in opposing parts, numerator and denominator, so they reduce out, and we get 28 times 60 and a pi, so 1,680 pi radians per hour. So that tells us that the angular velocity of that water wheel is 1,680 pi radians per hour. That angular velocity is equivalent to 14 rotations per minute. The second thing we have is that our radius of the water wheel is 10 feet, but we want miles. So the radius, so r is equal to 10 feet, but we want miles. And we know that there are 5,280 feet in 1 mile. And we want to convert r from feet into miles. So our feet are in the numerator in r, so we need feet in the denominator of our unit fraction. So we get 1 is equal to 1 mile divided by 5,280 feet. So our radius is 10 feet. We make it a fraction over 1. Then we have 1 mile over 5,280 feet. And our feet are in opposing parts of our fraction, numerator and denominator, so they reduce out. And we get 10 over 5,280 miles, or mile, and that reduces to 1 over 528 miles. So 10 feet is 1/528th of a mile. So then finally, our velocity v is equal to r times omega, which is 1 over 528 miles times our velocity, omega, which is 1,680 pi per hour. So then that gives us 1680 pi over 528, and then our units are finally what we want, miles per hour. So putting that last chunk into our calculator, 1680 pi divided by 528 gives us 9.999. So it looks like the speed of the river is approximately 10 miles an hour. So v would be about 10 miles per hour.